So in this video, we're going to work on a problem from 2018, a free response question. We have a function on the left, which is the derivative, sorry about that, which is the derivative of a function right here. So this is f prime. And we know that at -2, the function has a value of 7. That's basically the only thing that's given. We need to find the function value at -6 and at 5 for the first question. So how do we go from the derivative, f prime, which is the function shown here, to the actual function itself? What can we do to the derivative to get the function? Is there a way to undo the derivative? Yes, there is. That's actually the antiderivative of the integral of a function will give you, the antiderivative of a derivative will give you just the function itself. Now, we don't know what the function is. We don't have an expression for the derivative. So we can't just integrate to get an expression for the function itself. Instead, what we need to do is we need to remember that there is another meaning for the integral or the antiderivative, and that is that it is the area. It's the area under the curve. And you can get that by subtracting the antiderivative of the function in the integral at b minus the antiderivative at a. So in other words, if I integrate, let's see, we want to find f of -6. So if I go from -6 to -2, I can easily find the area from the picture, and that area is going to be equal to the function at -2 minus the function value at -6. We can easily, like I said, get that area of what is this? Let's see, the area under the curve. That looks like a triangle to me. So this is a triangle of base 4 and height 2. So it has an area of 4 times 2 divided by 2, which is 4. And f of -2 is 7, so we can now easily get f of -6, which I hope you can see is 3. So we have solved for the function value at -6, and now let's see if we can figure out what to do to find the function at 5. So we're going to do something similar. We need to integrate the given function, and somehow one of our limits has to be 5, which is all the way over here. And because we know what is the function at -2, that should be the other limit. So we'll go from -2 to 5, and again, this will be the area, the net area under the curve from -2 to 5, or at the same time, the antiderivative of the function in the integral at 5 minus the antiderivative of that function at -2. So remember that even though I say the antiderivative of this function, keep in mind that this is a derivative. So when you do the antiderivative, you're just basically doing the function itself. So this time the area is just a little more challenging. It's not too bad. is going to be half of the area of a circle of radius 2. So that is pi times r squared divided by 2, minus the area of another triangle. This time the triangle has a base of 3 and also a height of 2. So that is 3 times 2 over 2, which is 3. F of 5 is what we want, and f of negative 2 is 7. So work this out, and you will get an area of 4 plus 2 pi. Am I doing that right? Let me check. 7 minus 3 is 4. And yes, so I believe this is correct. Okay, so that's our first question. For question number 2, it's asking on what intervals is f increasing? Justify your answer. So what can we do to state the intervals where the function increases? Which function? Well, the function whose derivative we have graphed here. So, well, remember that if you know the derivative, which we know, we can easily tell if a function is increasing or decreasing. We just need to do a number line. We basically look at the derivative and ask, when is it positive, when is it negative? It's positive whenever it's above the x-axis, and obviously negative when it's below the x-axis. So here and here the function is positive. So it's positive to the left of negative 2, and it's positive to the right of 2. And it's negative in between. So we can use our graph here to justify when the function is increasing or decreasing. F of x is increasing from negative 6 to negative 2. This graph doesn't go all the way to infinity. The domain starts at negative 6. And also from 2 to positive 5. So it also ends at 5. It doesn't go all the way to infinity. And it's decreasing in between, so from negative 2 to 2. So that was an easy question. What about the next one? Find the absolute minimum value of the function on the closed interval from negative 6 to 5. How do we get the smallest value of our function? Well, we know the value at negative 6. We found that in part A of the problem, and that value is right here, which is 3. And then we know that the function is going to increase, right? How much does it increase as we go from negative 6 to 2? Well, it increases by this area, which we found to be 4. So from from positive 3, the function will go up 4. This is part C. And then the function will go down this area, the area of the circle, basically the area of the half circle, which is 2 pi. Again, we got that area before. It's up here, 2 squared times pi over 2, which is 2 pi. But we are going to decrease. Now, after decreasing, after we go past that area, the function is going to go up again. So this would be the lowest point that we're going to reach, 7 minus 2 pi. Because after that, we're going to add a positive area, and the function will therefore increase. So this would be the minimum value. And they didn't ask you when you achieve that minimum value. but the minimum value would be at x equals 2. Because that is the point when you stop adding or subtracting area. Whew. All right, we're almost done. One more part. I'm gonna need a little more space. I'm gonna erase my diagram for the derivative. Sorry about that. So for part D, it's asking us to find the derivative, the second derivative, sorry, at 5, and then at 3. So you have to keep in mind that the second derivative is just the derivative of the first, okay, duh. But we have a graph. So I guess what I meant to say is keep in mind what you know, and we have a graph of the first derivative. So to figure out the second derivative at a point, it means you gotta figure out the slope of this graph that we are given. The slope of the first derivative would be the value of the second derivative at a specific point. So at -5, which is right here, I said go turn into a pen. Okay, at -5, can we tell what's the slope of the first derivative? That will be the second derivative. Okay, so the slope of the first derivative at that point is easy to obtain. That's a straight line. It's going down to and over 4. So that slope is -2/4, which is -1/2. Yay! Now, what happens at 3? Can we tell the slope of the function when x equals 3? Well, hopefully you realize that at this point, to get the slope of the function, we won't be able to do it. This is undefined. Why is that? Because this is a cusp or a corner. And so when you try to get the slope at this point, if you're coming from the left, the slope is going to be some positive number. If you're coming from the right, the slope is going to be some negative number. And so the derivative is not continuous at that point. So let's be careful. The derivative of this function is not continuous, meaning the second derivative is not continuous. So the slope does not exist at that point. Okay, so with that, we have gone through all the parts of this question. Hope you find it helpful. And I'll be back with more. Thank you for watching.